Hey Phys Kids, Campbell here. In this video on electrostatics, we're going to talk about the basics of the charge model. Now, hopefully you've done an electrostatics experiment already, or at least have some background knowledge that there are two types of charge, and these charges exert forces on each other, and like charges repel each other, and opposite charges attract each other. Now, the source of that charge, we call them positives and negative charges, come from the protons and electrons that make up atoms. It's important that you remember that protons are in the nucleus. They're glued in the nucleus with those neutrons, whereas the electrons are moving around that nucleus in electron clouds. That's important because when ions occur, when we get things that are charged, it's because electrons have been added to or removed from that material. If an object has no charge, like no net charge, then it has an equal number of plus and minus charges. So it's an equal number of protons and electrons. But if something has a positive charge, that does not mean it has more protons. What it means is it has less electrons. Protons are stuck. They cannot move. If I have a positive charge, it means I have removed electrons from the atom. If I have a negative charge, it means that I have added more electrons to that material. So a negative charge is more electrons, a positive charge is less electrons. It's all about the electron. The symbol for charge is Q, and you'll see it sometimes as a little q or a big Q, but don't confuse it with Q, heat, from thermodynamics. When we talk, though, about fundamental charges, we use the symbol E. E is called the fundamental charge, and what it is the smallest charge possible, which is the charge on an electron or proton. The magnitude of that charge is 1.6 times 10 to the negative 19th coulombs. It's not plus 1 or minus 1. It is actually 1.6 times 10 to the negative 19th coulombs. The unit is coulomb. And that is the smallest charge possible, the charge of one electron or one proton. Now, because it's the smallest charge possible, all magnitudes of charges have to be a multiple of that number. So that means if I want to know the number of electrons possible, the number of electrons that have been added to a material or removed from a material, then I'll take that charge and I'll divide by 1.6 times 10 to the negative 19th. A couple other things you should know is that the mass of an electron is teeny tiny, 9.11 times 10 to the negative 31st. The mass of a proton is also super tiny, but compared to an electron, it's massive at 1.67 times 10 to the negative 27th. Very, very tiny particles, right? You don't just see electrons and protons with the naked eye if you have just one. Now, there are two types of materials, and those materials behave differently when it comes to the motion of electrons. There are conductors where electrons are free to move. We call metals a sea of electrons, and it's because the electrons don't have to hang out with their nucleus. In a material, they're like, hey, dude, I'm going over there. Mom, I'm going next door to some other atom, some other nucleus. So electrons can move around, and in fact, in conductors. And that's why we use conductors to conduct electricity in our homes. We have copper wires because copper is a great conductor. It allows those electrons to move freely, and electricity is the motion of electrons. An insulator is an opposite of a conductor. It's where the electrons are strongly attached to the nucleus, so they cannot move around freely. Now, that doesn't mean they don't move. It doesn't mean that usually what happens is if I bring another like charge, they kind of rotate. They're forced away, but they can't run away like a conductor, the electrons could. Also, with insulators, you can charge an insulator. You can add a charge to an insulator or remove electrons from an insulator and give it a positive charge. And insulators are great at holding charge because those electrons can't go anywhere. Once they're put on that surface of the insulator, they're stuck. If we take a look at moving a charged object near a conductor, you can see that if we move a negatively charged object, those electrons actually physically move to the opposite side of the conductor. If we move a positively charged object, those electrons will come running up to the positive charge. So those electrons are free to move. Notice the protons are not moving. The positive charge, those nuclei are not moving. What's moving are the electrons. But in an insulator, the electrons aren't free to move to the opposite side of the metal, or the material, I should say, but what happens is the molecules torque. So some of the molecules, if they can, will rotate. Others, the electron clouds will kind of get forced away if I bring in a negative charge, or forced towards if I bring in a positive charge. So different scenario. It's not that the electrons can't go anywhere, but they aren't free to move away from the nucleus. They're stuck to the nucleus in an insulator. Now, most things are somewhere in between a perfect conductor, where I have free roaming of electrons, and an insulator where they're totally stuck. So, how do you charge an object? Well, the law of conservation of charge, which is a fundamental law of physics, says that charge is conserved. What that means is that when you're charging something, the electrons aren't destroyed in the charging process. Electrons cannot be created or destroyed, so they just get shuffled around from one thing to another. Let's take a look at that shuffling by looking at some charging processes. Let's go to the tape. This device is called an electroscope. An electroscope is great for showing if an object has charge. It has a metal pole connected to some very lightweight metal leaves. If an object is charged, the leaves will move apart because the like charge is being pushed into the leaves, which causes a force of repulsion, and they separate. Now, I have some objects here. I have a plastic rod, and I'm going to bring the plastic rod over to this ball here. You can see nothing happens. So this plastic rod currently isn't charged. I'm also going to bring over some fur. So this is some rabbit fur, and if I touch the ball, you can see nothing happens. So currently, these two objects, all these objects are electrically neutral, which means that they both have the same amount of protons as electrons. However, I can do what's called charging by friction. So if I rub this rod in this fur, I can pull electrons off the fur and deposit it on the rod. How do I know it's charged? Well, if I bring it by the electroscope, watch those leaves move. See how they move away from each other? Now, notice they don't stay that way because I didn't touch the object. If I want the leaves to stay apart, I need to charge them and leave the charge there. So I do that actually by touching the object, and now notice the leaves are apart. Touching the object with a charged object is called charging by conduction. There's actually contact. And what I did, this had a negative charge, and when I touched the ball, I put a negative charge on those leaves. So some of the electrons jumped from this rod into the metal, and they moved down. They forced electrons down into those leaves, and now those leaves have negative charge, and they're repelling each other because they are like charges. Now, if I bring the fur, we'll see if this still has any charge left. The fur should have an equal but opposite charge. So if I bring the fur close, the leaves should start to go together. It did a little bit. You can see sort of a little bit going on there because the fur should have an equal but opposite charge to the rod. Now, if I want to discharge, we are great for electrons. So if I touch the ball, I pull the electrons out of those leaves because they want to get out of there. They're repelling each other. They run up into me, and you are a great conductor of electrons. And now I've made it neutral again. So that's charging by friction first. Rubbing, great way to charge insulators, and conduction, charging by contact. So the first thing you saw is me charging by friction. Friction, you can charge insulators and conductors, but it's really the only way to charge an insulator. And what happens is you're rubbing objects together that have different affinities for electrons. The affinities for electrons, we call that electron affinity, or the love of electrons, is represented in a series called the triboelectric series. So a triboelectric series lists materials in the order of affinity. Now, you saw me work with rabbit fur, so I don't see rabbit fur on here, but it's like hair, right? Rabbit fur, hair. The hair of a rabbit. Remember I said that it lost the electrons and gained a positive charge? Well, it doesn't have a high affinity for electrons, whereas the plastic rod I used was actually polyethylene. Polyethylene is a type of plastic polymer, and it loves electrons. So it stole the electrons. Well, okay, it didn't steal them. The hair gave it to them. The rabbit fur gave the electrons it had when I rubbed it to the polyethylene. Now, it didn't give up all of its electrons. The more I rub it, the more we're actually going to transfer electrons. But in a triboelectric series, you can determine what to rub on what and what charge they're going to get based off their electron affinity or their love for electrons. The other thing I did, once I charged that by friction, I then touched the electroscope and transferred charge to the electroscope. So that's charging by conduction, and it only works for conductors because the electrons actually physically have to move. So in charging by conduction, there's contact. I had to touch the electroscope to leave the charge there. And so we're touching a charged object to the neutral object. So here, in this case, this is a positive charged rod. I had a negatively charged rod. And in this case, what happens is the electrons get pulled up towards that positively charged rod, and they neutralize some of that positive charge. Not all of it. They can't do that. What happens is the charge flows until they end up with the same amount of charge. So when I charge by conduction, there's contact, and the objects end up with the same amount of charge. So anytime we have charge transfer, how much charge transfers is really based off the material and the size of the object. But if they're the same size and the same material, then the net charge is just going to be an average. So what I mean by that is, because charge is conserved, the net charge has to be the same before and after. So if I start with 12, say here I have positive 12 charge, when I touch these two materials together, I still have to end up with a positive 12 charge. So what's going to happen if I touch this sphere to this sphere is electrons are really going to flow, right? So it's really, electrons are going to be moving over here to neutralize some of that positive charge, and in the process leaving that sphere B with a net positive charge. But in the end, the total charge has to be 12. So if I take 12 and I divide by 2, because I have two objects here, it's going to be 6. So charge flows until each objects have the same charge. And so if I start with 12, I have to end with 12. And so that means each sphere is going to have 6. So I touch my 12 to my neutral sphere. The electrons move from this sphere over to here until they both have the same identical charge, and then I separate them and that charge is stuck. Now my net charge is still 12, but each sphere has 6. So what I'd usually do is, depending upon how many touches there are, how many objects there are, what I do is I take the net charge and I divide by the total number of objects, and that'll tell you how much charge there is on each. But it's never 0. This one is not going to completely neutralize that and make it 0 and this plus 12. That just doesn't happen. It can't happen. Charge flows until the charges are equal. Well, it's really till the electric potential is equal, but that's a whole nother topic. There's one other way to charge, which I didn't show you in the video. It's a little more complicated, and it's called charging by induction. And this only works with conductors as well, because we need electrons to flow. Now, we call this no contact, but that just means that there's no contact between the charged object and the neutral object. In conduction, there's contact between the charged object and the neutral object. In induction, there's no contact. But there still has to be contact, just not with the charged object. So what we do is we use what's called a grounding wire. A grounding wire is just a conductor that connects that neutral object to the ground, or some sink for electrons. You could be the grounding wire when in charging by induction. So the Earth loves electrons. You love electrons. And remember, I said that when you neutralize the electroscope, you just got to touch it because you love electrons. The ground loves electrons too. So when we charge by induction, we have contact between an electron sink, or what we call a grounding wire, and the neutral object. But there's no contact between the charged object and the neutral object. What happens when we do it this way is we can get objects with opposite charge. Conduction, it's the same charge, but with induction, it's opposite charge. So let's look at how this works. So we're going to start here. I have this sphere on an insulating stand. If I bring a negatively charged rod in here and I don't touch it, remember, it's kind of like the electroscope, what happens is the opposite charge accumulates as far away from the charged rod I brought in as possible. So those electrons move over there. That's actually called polarization. Polarization is when I get a separation of charges. Now, right now, they can't go anywhere. As long as I don't touch that metal sphere, I'm just going to keep, and I keep that negative rod there, I'm going to keep this polarization. But if I stick a grounding wire to this sphere, what's going to happen is now the electrons have a path to get away, right? They're feeling the force of repulsion from that negatively charged rod, and if there's a way to escape, they're going to go running. So they go down into the ground. Now, if I keep the rod there, those electrons will stay in the ground. So then if I disconnect that wire, then those electrons are stuck in the ground. They don't have a path back to that charged that sphere. And so then if then I remove the charged object, that charged rod, I'm going to leave the sphere with an opposite charge, so the positive charge. Now, if I connected the grounding wire and then I took this away, what would happen is the electrons would just go back up there, right? Because when they're in the ground, they're still feeling a force of repulsion of the electrons, so they're going to want to get to a positive charge. They'd be attracted to that charge. So if I removed the rod, the electrons would just go back, and then I wouldn't result in a charge. So I have to disconnect the grounding wire while that charged rod is present. And if I do that, I will be left with objects that have opposite charges. So that is charging by induction. No contact between the charged object and the thing I'm trying to charge, but I have to have a grounding wire. And I will get two oppositely charged objects. So let's take a look at this. Which is charging by induction and which is charging by conduction? Oh, look at you, you grounding wire, you. Well, if you said A was conduction because there's contact, and notice that when this happens, they both end up with the same charge, so they both have a negative charge. And this is induction. Lost some light there, sorry about that. Induction, because there's my grounding wire, right? And the electrons are coming out of the grounding wire towards that. And now I have oppositely charged objects. You were correct.